Hello and welcome to Engineering Tomorrow's 3D Printing and Product Development Lab. In this lab, you'll be learning about manufacturing engineering by exploring the 3D printing process. So to start off, I'll tell you a little bit about myself. My name's Olivia Janicki, and I'm originally from Staten Island, New York, and I went to college at the University of Notre Dame over in Indiana. There, I studied mechanical engineering with a concentration in Irish literature. I graduated in May 2020, and 3 weeks after graduation, I started my first full-time job at a company called ASML in Wilton, Connecticut. There, we make the machines that make computer chips. These machines are called photolithography machines. They're about the size of a school bus, and they cost $150 million. You can see a picture of one there on the bottom right. I work in a clean room wearing a suit like the one you see on the top right. And we wear these because a single particle of dust can be catastrophic in the chip making process. So if even the smallest speck of dust falls out of our machines and lands on the chip pattern, once light passes through and is reflected onto the wafer, it becomes a huge spot that renders the computer chip completely useless. And by the time it's discovered, hundreds of chips will have been ruined. I work specifically as an optical production engineer, which is a type of manufacturing engineer. So I'm responsible for the assembly process of just one of the sensors in these machines. I try to make our process more efficient and produce a higher quality product. I specify what tooling we need, what data we need to collect during the build process, and what type of training our technicians should have. So if you have a newer computer or iPhone, there's like a 99% chance that the ASML machines made the chip that's inside it. So the reason I got into engineering is because in high school, I really enjoyed AP math, physics, and computer science classes, and I knew I wanted to use those skills to make products that directly impact people's lives. I chose mechanical engineering because freshman year of college, I talked to professors in different majors and looked ahead at what my classes would look like, and mechanical engineering just interested me the most. It's also a pretty broad major, and since I didn't know exactly what I wanted to do for a career when I was a sophomore choosing my major, it seemed like something that would just really keep my opportunities open. And I decided to work in manufacturing because senior year of college, I loved working in the machine shop on campus, seeing how things were made and getting to do some hands-on work. ASML recruited at my college senior year, and their work just sounded really cool to me, so I took the job. I had no idea what working on lithography machines would be like until I started working at ASML. So don't worry, you don't have to have everything all figured out right away, because I definitely didn't. Engineering Tomorrow curriculum is developed by professional engineers and engineering students. Here's the team that developed this lab. And I also did a little bit of work on an earlier version of this lab back in 2017 after my freshman year of college. So this is a fun one for me to present. So before we dive into the 3D printing process, we're going to step back and think about all the steps that are involved in getting a new product into the hands of customers. So some of the steps include defining and refining your idea, research and design, purchasing materials, building your product, testing the product, and marketing the product. So here's a question for you to think about. Who do you think might have good ideas for new products or product improvements? Ideas for new products can come from everywhere, but some possible answers could include customers, engineers, scientists, and salespeople. Interviewing customers who can share their needs is a really, really good place to start. A product absolutely has to satisfy your customers' needs to be successful. So many times, companies employ a series of product managers who are each an expert on a particular product and maintain close relationships with the customers who use the product. For most new product development projects, a dedicated team is formed with a collection of personnel from various functional areas. And these individuals include manufacturing engineers, design engineers, materials engineers, and marketing and salespeople. So you can see that there's a variety of roles that engineers can play in a company, and that's whether you studied chemical, civil, electrical, mechanical engineering. So today, we're going to talk specifically about manufacturing engineering, which is what I do. So manufacturing engineering is how we make stuff. More specifically, how we transform raw materials into finished goods. manufacturing engineers have several responsibilities. I told you a little bit about mine, but they design and operate the manufacturing systems for a product. They choose the best technologies and processes to manufacture different products. And they also design the factories that will produce the product and manage the running, maintenance, and continuous improvement of the manufacturing process. So in this video, we're going to hear about the personal experience of a manufacturing engineer.
My name's Jonell, and I'm a manufacturing engineer at Space Systems Loral in Palo Alto, California. Space Systems Loral makes commercial satellites for all different kinds of companies. They do things like TV, radio, some weather satellites. My work is involved in making sure that we get everything done on time. A big part of that is making sure the technicians have what they need. You can see some of the thrusters up there. The thrusters aren't fueled up yet. I went to junior college and I was just taking classes. My advisor asked me what I liked to do, and I told him I liked, some science stuff and gave him like general background. And he told me I should be an engineer, and eventually I transferred to San Diego State, and then I got a degree in engineering. A typical day for me is like, I come in, I go into what we call our laboratory, and I walk around, I'll talk to the technicians, I make sure that they have everything they need as far as being able to understand drawings, having all the parts, having everything from chemicals that they need to do different processes. We do a lot of calculations on our efficiency and whether or not we're making things at the correct speed. And we have what's called a design engineer. And they basically design a lot of the satellite and different parts of it. And sometimes their drawings aren't totally clear. My job, if the technician says, hey, I don't understand this drawing, then I have to kind of interpret it or figure it out or call the designer and see if he can explain it to me. And then after I understand it, I'll go and try and put it in layman's terms to the technician. I maybe don't apply like everything that I learned in calculus and algebra, but I do apply like not giving up on a problem or sticking with it, or just because something's difficult, I don't give up. The classes that would have helped me in high school probably were obviously the math classes, even though I was bad at it. English classes, because you do a lot of writing. You do a lot of just writing emails and stuff, and you don't want to sound dumb when you have to write to your manager or somebody else's manager. I like interacting with people and helping people, and if I was like recommending anything to a high school student today, I would say take as many classes as possible and as many different things so you get a taste of everything and you can find out what you really like.
So you can see from this video that some of the most exciting parts of working as a manufacturing engineer are that no 2 days are the same, and you can interact with all different types of people from different functional areas. And you can use the various skills you've gained, both just as a person and as an engineer, to do your job. So we're going to go over the 4 primary manufacturing processes. These are additive, subtractive, forming, and casting. So additive manufacturing is when you start with nothing and then you build up a design. Subtractive manufacturing starts with a block of raw material, any material, and removes or cuts away material to make a design. Forming is when you're applying force to a raw material to create a shape. And then finally, we have casting, which liquefies the raw material and then puts into a mold to create a design. This is how a lot of like small plastic parts are made. Plastic injection molding is a type of casting. So I have a question for you to think about. What type of manufacturing do you think 3D printing is? All right, so if you guessed additive, you're correct. And that's because we're starting from nothing and building up a design layer by layer. All right, so now we're gonna get more into 3D printing. So 3D printing is a type of additive manufacturing, as we just discussed, and it's a technology that's been around since the mid-1980s, but it's playing an increasingly bigger role in how we design and build products today. So here's a short intro about 3D printing and its applications.
What is 3D printing? 3D printing refers to a variety of processes in which two-dimensional layers of material are deposited and joined. one upon the next, to form three-dimensional objects. This process is also known as additive manufacturing, and is a fundamentally different way of producing parts compared to traditional, subtractive, or formative manufacturing technologies. How does a 3D printer work? The 3D printing process always begins with a digital 3D model that is converted into an STL file. This model is then sliced by the 3D printer's software into thin, two-dimensional layers and turned into a set of instructions, known as a G-code, for the 3D printer to execute. From here, the way a 3D printer works varies by process. For example, desktop FDM printers melt plastic filaments and lay them down onto the print platform through a nozzle. Large industrial SLS 3D printers use a laser to melt thin layers of metal or plastic powders. Plastics are by far the most common, but metals can also be 3D printed. Depending on the size of the part and type of 3D printer, a 3D print usually takes about 4 to 18 hours to complete. However, 3D printed parts often require some post-processing to achieve the desired level of surface finish.
Okay, so this video touched a little bit on CAD, or computer-aided design. So if you studied mechanical engineering or even civil engineering in college, part of your coursework would include learning these CAD programs, which is how you design 3D models, not just for 3D printing, for all types of designs, but you'll be using CAD in your lab today. And yeah, that's something you would study in college. This video also touched on the different materials that are used in 3D printing. Like metal is a pretty cool one that you can use, but engineers and scientists are also exploring how to use 3D printing in medicine. So like creating custom implants like hip joints, external prosthetics like hands or fingers, and scientists are even researching how to use the 3D printing process to manufacture living organs such as a heart or a liver. And this research is still in the pretty early stages of development. 3D printing isn't always the best manufacturing technology to use, but it can be a great choice if your requirements include fast, inexpensive, and custom complex geometries. With 3D printing, once a part is designed, an object can be printed and ready for use in just a few hours, which is a huge advantage for something like prototyping. Items can sometimes be created in just one step with minimal post-processing. There's a lot less material waste as opposed to like subtractive manufacturing, where you're just cutting and cutting away material. And you can make complicated designs with tremendous accuracy. So like I said, if you need like a test part, 3D printing is great. We do that a lot at my job, just to kind of like visualize how things will fit together. 3D printing is perfect for that. 3D printing is also great if you're in a low resource area where you don't have a full machine shop available to you. So for example, some companies are looking at putting 3D printers on ships or even in space so the crew could print any tools they may need. All they would need is the design file and they could print it right out. So these benefits are pretty important to companies because there's lower costs and less effort needed to make a product. 3D printing is infinitely customizable. Customization doesn't really increase the cost very much. And rapid prototyping makes iteration and testing process easier and cheaper because you can just churn out prototypes if you needed to. All right, so we talked about computer-aided design, CAD, and with that comes another step, and that is engineering drawings. So drawings are important when it's time to send your design to a manufacturer like me. I get sent engineering drawings all the time, and that's what we go off of. That's how we base our whole assembly processes so we can meet the specifications on the engineering drawing. So they specify the shape, the size of the part, the materials you need, and even how you will assemble the design if there's multiple parts. You should include as many views as necessary to showcase each unique side of your design. And these can include top, front, and side views. We'll get into that a little bit more in the next couple slides. And you need to document all the parts necessary in building the design and make sure that they're dimensioned and labeled with a specific measurement and units. Drawings are really cool because they serve as a universal language among engineers. So they're standards, so all engineering drawings follow the same set of rules. So any engineer can read and understand them, no matter what company you work for or even what language you speak. Okay, so we have a little activity here so we can practice some engineering drawings and using the different views. So the image on the left here goes over what the top, front, and side views of a cube would be. So for example, the front view shows a depiction as if your eye is only viewing the cube directly from the front. So like a can of Pringles viewed from the top would look like a circle, but viewed from the side, it looks like a rectangle. So kind of use that visualization, and we have a little practice activity here. So if you look at the isometric view, and there's 3 different projections, so which of those pictures do you think is the top view based off of your isometric view? And then see if you can decide which would be the front view, as if you're looking at that bracket head on. And then which of these views do you think would be the side view if you're looking at that bracket from the side? So see if you can figure out which one is top, front, and side. So yeah, we know the top one, we can only see those 2 holes from the top. So it's important to have our top view. And you could dimension those circles and say what diameter they are in that view. And that's our side view. So just like it's important to be clear while speaking so that your message can be understood, it's important to have drawings that communicate what you want to be created. This is why engineering drawings have multiple views. It allows for clarity. So we're going to try this out. So if I give you only this one view that you see on the slide here, what do you think this is? So it could just be a plain box. It could be a tin for holding cookies. It could be an envelope. We don't know because all we see is this little square here. So the bottom right picture is what the previous slide showed. And now with multiple views, it's pretty obvious that this is a tissue box. So you can see how having multiple views gives more information and therefore more clarity for what is being designed. And just like having multiple views gives a better understanding of what needs to be built, so does dimensioning. So we'll look at this drawing here, and let's have some guesses for what you think this might be. So since we have no idea what size this is, it could be anything from a step stool to the Arc de Triomphe in France. So now we can see it's pretty clearly a step stool and not a giant arch. It's only 5 inches wide and 5 inches tall. So it's definitely important to communicate the proper size and also units of what you're designing. Like, it's very important to be careful going between like inches and centimeters. All right, so let's start to talk about your task for your lab. So I'll just walk you through the design challenge that you'll be documenting in your student interactive workbook. For your task today, you'll be working on some rapid prototyping. So you'll begin by creating a Tinkercad account and learning to use the software. There's like a simple activity so you can familiarize yourself. Tinkercad is a very simplified version of computer-aided design. It's pretty easy to use. And then you'll identify a problem in your home that you'll design a solution for. So I actually did a similar project to this in college, and I designed a coaster that perfectly fit my favorite cup, and I put my initials on it. So you should definitely take advantage of how customizable 3D printing is. Like I said, it doesn't really increase cost or time to like add some words or designs. So definitely have fun and be creative with that. And if you're having trouble thinking of what to design, like we talked about in the beginning of the lab, interviewing customers is a great place to start. So ask your parents, siblings, or friends, what are some issues or inconveniences they face in the household, or you could even just Google common household problems. And this could give you some inspiration for your design. Don't worry about the design solution right at the beginning, but you should focus on first finding your problem. So what do people wish that there was a solution for? And then you can build off of that. And then once you've identified a problem that needs solving, you'll follow the remainder of the engineering design process outlined in the workbook. So some important things to confirm when you're finished doing your design, and I'll show you this in just a second, but you need to make sure that your piece is flat against the work plane. You can see if this is the case by checking that your Z dimension is 0. This is important because 3D printers can't print into thin air. As magical as they are, they need to be depositing material onto a flat surface. You need to make sure all of your pieces are grouped together. Otherwise, the 3D printer will kind of reorganize shapes for you and you won't get exactly what you planned. And then make sure your design is also within the size constraints specified. So 10 centimeters by 10 centimeters and then only 2 centimeters tall. We need to limit the size of the prints we make just because of the size of our 3D printers and the number of students whose projects we're printing. The bigger the object, the longer it takes to print. Like bigger prints can take like up to 48 hours to print. So we're trying to limit that a little bit. If your actual design is bigger than these dimensions, you can just create a scaled down model of your actual design. Engineers often build prototypes, which are smaller versions of their final design, and using different materials just to see your design concept in action. You could show the design to your customer or other engineers to get feedback before moving forward with a bigger and more expensive final version of your design. And so Engineering Tomorrow will print out your designs for you. And once you receive your print back from us, you can complete the testing and evaluation of your design. So just note that teachers should collect all the student files and send them to us for printing. And there's some instructions for how to do this located in the student workbook and the teacher guide. And we're very excited to see what you create. Okay, so now I'm just going to do a little demo of just how to make sure that your design is all correct in Tinkercad. Here we are in Tinkercad now, so I'll just do a little demo of how to make sure that everything is set for your final design. So you can see here I've created like a little bit of a measuring teaspoon, and you can see all your different views like we talked about, you know, top, front, bottom, or you can just drag around on this box so you can get a good view of what you're making. But so right now I just have a bunch of different shapes on here and they're not grouped. So what I want to do is just drag a box to make sure that they're all selected and hit group. Oops. Yeah. So now these will all print as one teaspoon and not like a circle over here and a rectangle over on the other side. They'll be all together. And then the other thing you can see is that I have my piece kind of floating in midair, which is what you don't want because your 3D printer will become confused with that. So you'll want to take it and then drag it down. And that number that's going down on the side down to 48, that's the Z dimension. So you want to make sure it's exactly 0. If it's negative, that'll also cause issues. Your 3D printer can't print below the work plane either. So you want to make sure it's starting at exactly 0. It should be okay if you don't have a perfectly flat bottom because the 3D printer will add a little support material on that can just be easily peeled off. And then, yeah, just make sure this height is about 2 centimeters and that you're not exceeding 10 centimeters by 10 centimeters in either of these directions. Yeah, so have fun with Tinkercad. All right, so before we finish up for today, I just wanted to show you a couple of 3D prints that I have laying around because I'm an engineer and I think 3D printing is, I mean, not just useful, but it's also fun. So there's a lot of websites. One of them online is Thingiverse, where you can see other designs that people have made and download them and print them out. You can also get some inspiration for your own designs. But one thing I have here is a little 3D printed Hogwarts. So that's something fun. And you can see like how intricate the 3D printers can be, and they can make such tiny little features. This isn't even like the most high quality 3D printer. This is like more of a recreational one that I used at school. And then like this would be a fun something to incorporate in your design challenge, but this is like a little screw that goes back and forth and has a nice texture on the outside. So, I mean, if your problem is that you need something to fidget with in your house, this would be a good solution for it. So if you like today's breakout, you might be interested in these topics. Rapid prototyping, we talked about, is when you design something and then you get a prototype out really fast so you can test it. Using other materials, so 3D printing with wood, metal, and biomaterials, and how 3D printers can print empty space is a good topic to look into. And then the types of engineering relevant to today's 3D printing breakout: manufacturing engineering, which we talked about; industrial engineering, work closely with manufacturing engineers to make processes more efficient, analyze data related to manufacturing; materials science, if you're interested in choosing what types of materials work the best with 3D printing and other types of manufacturing; computer science, if you're interested in like the programming of software that we use to control 3D printers or create computer-aided design programs; mechanical engineering, if you really like designing your new product, that would be mechanical engineering; and mechatronics if you're interested in using robotics to control machines, like a 3D printer is an example of mechatronics. All right, so thank you so much for joining Engineering Tomorrow today. 3D printing is so much fun, and it's also really a useful skill to learn. Please send us pictures or post your designs because we love seeing all the creative ideas our students come up with. And I hope you gained a little more interest in engineering today, and you saw how much room there is for innovation in the field of engineering, and that's why we want all of you to also become engineers. So thank you so much.